Okay, so Green's theorem, Wavefield separation. Which Wavefield separation are we talking about here? We're talking about separating the reference wave from the scattered wave and deghosting. Deghosting is a wave separation of up and down, yes? So that's what we're going to look at. So that's it. That's what that says. We're also going to separately be looking at Green's theorem for wave prediction. We're predicting a wave inside a medium. In other words, you have sources and receivers on the Earth's surface. If you want to know what a receiver would record if it was in the subsurface, and what a source and receiver would predict if they were in the subsurface from surface measurements, Green's theorem gives you a way to predict a wave field. So it gives you ways to separate wave fields, and different for a different spin on Green's theorem gives you a wave prediction, which leads to a form of migration called Claerbout 3. Okay, which we'll have a lot to say about. Okay. So here we have, this is merely an example, an acoustic example to illustrate something. Imagine you had a single frequency, heterogeneous acoustic medium, and some localized source with some time-dependent, some wavelet in source signature there. And then imagine the following, that the actual velocity configuration, C of R, is characterized in this way, 1 over C0 squared times 1 minus alpha, where C0 is called a reference, and then this is some perturbation. This in alpha characterizes where the actual velocity and this reference differ. Why is it defined this way? The reason it's defined this way is it brings this parameter into a numerator, and then when it's on the other side, that parameter and the wave field are both in the numerator, and so linear relations are easier that way. That's why it's defined that way. Okay, you could have imagined writing C of R is C0 times 1 plus alpha, 1 minus alpha. That turns out to be easier to write, but worse for processes. Okay, if you want to see that, what I just said, I suggest you look at Sholem Raz, 1981 Geophysics. C of R is C0 times 1 plus a perturbation. Then along, realizing how complicated that was, Clayton and Stoll does this kind of thing. Okay, it much simplifies linear and beyond. Okay, so now what we're going to do is we're going to take this actual velocity configuration, substitute it in here, and then put the part that has to do with alpha on the right-hand side. Like that. And now we want that equation, del squared plus k squared p is rho. Now we have that. Del squared plus k squared p is rho. What's rho there? Rho is anything. Terms. Doesn't matter what. Whatever rho is a function of r and omega. Here is the solution, yes, for all space. So with this association like that, and then the next slide will just mention that G0 story. This just shows how it would look like if you assumed elastic. It would just have, instead of alpha, you would have alpha, beta, variations in shear modulus, bulk modulus, and density for the PP, and for the VPS you'd have changes in shear modulus and density. Okay, you understand it? But it's still rho. It doesn't care. The whole thing is that what you're going to see for the wave separation, methods, like predicting the reference wave from the scattered wave, predicting both of them without injuring either one, deghosting, it does not care. Those methods do not care on the nature of rho. It could be acoustic, elastic, dispersive, absorptive, it doesn't matter. Okay? Those methods are independent of that. When you go to wave prediction, for migration, you'll see it does care. Okay? Okay? For Green's theorem, for wave prediction, it cares. And then we're going to see how, from that same starting point, the inverse scattering series, from the same exact equation, will not care about rho for wave prediction. You understand? So it's very important for me to explain where those two separated, yes? From the same exact starting point. We haven't communicated that before, okay? I mean, before today.
There's no assumption about the relative size of alpha with respect to the reference medium velocity?
Or what's assumed, that's a good question. What's assumed is, for this model, is that rho, or let's say with alpha and all other things, that it's integrable. So if you have, like, let's say, our actual velocity, which is c0, and then c1 forever, this will fail. That simple model, that simple Earth will not be accommodated by what I just wrote. Let me explain why. Because the c0 is this, then the c1 has a perturbation, but it's forever. So alpha is from wherever the jump started to infinity. That's not integrable. You take 4, a number 4, integrate from 1 to infinity. So the assumption is that this with G0 plus is integrable. So we have to have tapers. In other words, we have to have, so you say, well, in other words, we're going to assume in practice there's a piece of the world that we're interested in. And what happens below that we don't care. So we'll assume it tapers after that because we don't get data back or it's below our, yes? But that's a good question. So it impacts the size, but also the extent. There are assumptions in that, in terms of what this model being valid. The model, I mean rho G0 plus, giving you the field. It has to be integrable, yes? Okay. And as I said, everything we do have assumptions. Thank you. So this is what we wrote right at the beginning. We said if you take the response to a single point rho, then you can find the solution, the causal solution to any rho, yes, within the conditions I just mentioned, as long as this is integrable, yes? So, but that can cover a lot of territory, yes? Because first of all, even if the real rho was that C0, C1 forever, our interests seismically are always confined. So what I assume beyond that is irrelevant. You understand? Beyond a certain depth. Okay, so let's make clear what this says. This is a very important statement. This is the solution for the field P everywhere R in the universe. And it integrates over all the sources in the universe. It says, if you want to know the field, this is what this form says. If you want to know the field anywhere in the world, I need to know rho everywhere. Let's remind ourselves what that means. In this same for elastic. It means I need to know rho. I need to know where the source was, its character. I need to know alpha. Well, if I need to know alpha, that thing has G0 and alpha, it means I need to know the velocity. Yes? So what it says, it's a very simple, it says, if you want to know the wave field in the whole world, you have to know the properties. You have to know what generated the wave, exactly, and all the properties in the world. That's what that communicates. Clear? Yes. Now, Green's theorem is going to give us something different. Let's say I'm not interested in the field everywhere. Let's say I'm interested only in a volume. Yes? Well, if you give me the characteristics everywhere, you'll still find it in the volume. You understand? But let's say, can't I pay something less? Do I need to know? That's where Green's theorem, 1826, was radical. No one would publish. He paid. He published his own paper. You understand? You understand? You got to be kidding, you know? So, that's the truth, okay? George Green published his own, took money, it was just rejected everywhere. There's never heard of that crazy thing. And so you could check, I didn't make that up. Yeah. So here's what Green's theorem says. Green's theorem basically is, everybody builds from someone. It comes from Isaac Newton, that genius. In other words, Isaac Newton said something extremely profound, which affects us seismically, of course, all the time. He said, the fundamental theorem of the integral calculus. He said, if you integrate a, b, f of x, dx, you do an infinite sum. This is a limit of a sum of f of xi, delta xi, right? You broke up some, if you think in terms of area, right? Area under a curve into little boxes, and then you took a limit as the boxes got infinitely small in width and infinite number. You add them up, that this is replaceable by phi of b minus phi of a. That's amazing, that there is a function that just cares about the endpoints. No, but this function, its derivative is f, okay? So that was the startling thing, that's integrating, summing something over an interval is replaceable by something else on the boundary, okay? The antiderivative, yes. That leads to this. In other words, Gauss took Newton and went to a volume. Gauss said, the divergence of a vector, dr prime on a volume, is replaceable by a surface integral of a dot n ds. Exactly Isaac Newton in 3D. Something integrated inside. Look at it. Yes? Is the antiderivative of this on the surface. Yes? Then this green is, now you put in two functions, let a equal psi grad phi minus phi grad psi, and you get this. The basic point here is there's a volume integral and a surface integral, okay? And it's saying you can integrate something on inside a volume and replace it by something else outside. Look, second derivative, first derivative. It all comes from Isaac Newton, yes? Okay, you get the point? So this is going to give you a different opportunity. Now, if you take, this is just an identity, some kind of function p, and this has nothing to do with any equation. This is just psi del square phi. Now we're going to get our interest in here, put p to be our p, that g0 to be our g0 in that simple case, and that's what it's saying. Take del square p and del square g0 from their previous equation, meaning there's g, in other words, take del squared g0 and write it as minus k squared g0 plus delta. Take del squared p and put it, all the things were on the right hand side. Whoop. In other words, replace in that integral del squared p by that stuff plus this on the other side, okay? And you get a an identity. That identity, first of all, the substitution of del squared g0 by equals minus k squared g0 plus delta did not depend on g0 being causal. It's an identity. In other words, that cannot be overstated. It's going to lead to migration theory, okay, that statement. In other words, it's just any solution del squared g0. You understand? You're just substituting its differential equation. When you write p is this, you're saying, here's some elementary causal, and now I have weighted sums on it. So I'm building an actual causal by a weighted sum of elementary causals. It's whole causal thing. This guy comes from a very different place. It's a mathematical statement. All you assumed here is that del squared G0 is coming from some solution to the G0 equation, yes? You're not calling on linearity and superposition of causal to make an actual causal, yes? Very different origin, and hence very powerful, you'll see. Migration theory depends on this being satisfied by non-causal. You'll see. So, now, that equation, that last equation, if you do all the substitutions with putting in for P minus k squared G0 plus delta, putting in here minus k squared P plus rho, the delta here from this asks a question. Is R in the volume? If R is in the volume, you get P. Yes. If R isn't, you get 0. Both are true, okay? So for R in the volume, this is going to lead to an expression for P in the volume, yes? For R in the volume. That's why it says P for R in the volume, come from Green's theorem, gives you the surface term, plus this, the k squared G0, and they cancel. So, first of all, a very important point is equation 8 does not care what solution you put in for G0, as long as it satisfies del square plus k squared G0 is 0. It could be causal, anti-causal, sum of causal plus anti-causal over 2. Any of the infinite number of solutions of that del square plus k square G0 is rho, you put that in there, it will give you P. Okay? So that takes some thinking, yes? But in other words, we never argue for superposition of causal like that, you understand? It's just a math statement. You substitute it for del square G0 minus k squared G0 plus delta. Any G0 that satisfies that equation will satisfy that relationship. That's all you assumed, okay? You didn't argue causality. So this equation, if among the infinite choices of G0, you happen to choose G0 plus, yes? You get a set of wave separation results, okay? That's the point. Where does that come from? You have, maybe it's on these slides. We have an expression for the field everywhere. The field for any R is that G0 plus rho integrated over the universe. I integrate over all the sources, I get the field everywhere, yes? But everywhere can be broken up into an integral on the volume plus everything outside the volume. That's the same as everywhere, yes? So this came from a different starting point, right? That came from there, yes? For a field, this gives you the field in any position, yes? It's just a breakup of that into the contribution from the volume and then outside the volume. In the previous slide, you had an expression for the field only in the volume. The P in the, why only in? Because when you substitute, there's a delta, and it says, is R in the volume? If R is in the volume, this plus this gives you P. If R is out of the volume, this plus this gives you 0, okay? So for R in the volume, so for R in the volume, by the way, this will be important for migration theory, still any G0 will work here. Yes?
So, rho has built into it P, right?
That's a good question. Yes, it doesn't matter here. It will matter. In other words, that exact question separates migration theory from inverse scattering theory. For migration theory, we don't ask we don't get personal about rho. It's a term. And you'll see how that leads to migration theory. If we ask the question, what about, doesn't rho care about P? You get the inverse scattering series and a whole set of different consequences. It's exactly that point that separates, yes? Whether you treat rho as a term whose detail doesn't matter, you're going to get conventional migration, you see? Yes? If you get into rho being whatever k squared alpha p or something, then you're going to get the scattering series and the inverse scattering series. At that juncture right there. Okay? Yes. So you'll see how it becomes migration in a minute. Okay? But that's going to be, we're going to focus on, so this gives you an expression for only the field in the volume. Because if you take R out of the volume, this gives you this plus this is 0. That thing gives you an expression for the field anywhere, including in the volume. So in the volume, this has got to agree with that. Yes? Okay. So that means that that surface integral must be the contribution for points R in the volume. The contribution to the field due to sources outside the volume is the surface integral. Let me remind where this comes from. This is an expression for the field in the volume. First, it says something very interesting. It says, if George Green says, I'll cut a deal with you. In other words, this says, you want the field everywhere, you got to tell me everything that's happening in the universe. That's it. You got to tell me all the properties of the universe and the source. George says something else. If your interest is confined to the field in the volume, I need to know the details of what's going on in the volume. Source in the volume, alpha in the volume. But I don't need to know, but just because I'm interested in the field in the volume doesn't mean the field only cares about what's in the volume. I draw some potato, which is my volume. The field cares about the whole world. Just because my interest is confined doesn't mean the field's interest doesn't care about outside. This gives you the influence. George said the influence of the sources outside the volume on the field in the volume is picked up by this integral. Surface information. Isaac Newton, there's a replacement of an integral by something on a boundary. Yes? Okay. So, in other words, this says that everywhere the field is due to sources inside and due to outside. This is also valid for R in the volume. Yes? So there's this plus this. Going back to the last equation, this guy's got to be the surface integral. Yes? So the surface integral with a G0 plus, I needed to pick G0 plus because that guy needs G0 plus. That guy won't work with G0 minus. You can't build a causal solution in terms of elementary causal. Yes? Yes, that is not Green's theorem. This is linear superposition. Yes? Different thought. So you have a very important theorem. This is well known in physics. What it says is, this surface integral, when you evaluate it inside the volume, gives you the contribution to the field inside due to sources outside. Born in Wolf, page 100, they call that the Extinction Theorem. Ross Hill at Chevron, he did his thesis on this kind of thing in physics, okay? Morse and Feshbach call it the way in other words, why Born and Wolf call it the extinction? Because this guy and this guy are the total field, their measurements. They're not measured due to field outside. That combination, when evaluated inside, extinguishes the contribution to the total field due to sources inside. Yes? So they call it the extinction theorem. Yes? Born and Wolf, page 100. The optics book, yes? Morse and Feshbach talk the half full, you know? They say it is the contribution due to sources outside, yes? We introduced this to seismic, 1990, with Seacrest, okay? For source signature, the paper. But the physics of it is not new. The seismic bringing was, okay? Just want to make that clear. So how does this get applied? Let's say you're in the marine case, and this is your reference medium. Reference meaning there's air, or it could be assumed to be a vacuum, and then water, and then there's earth. The reference medium here is going to be vacuum and then water. And then sitting on top of that is a source which makes earth, alpha, yes? So there are two sources then. What do you mean two sources? There's this reference, which is air or vacuum, and then water, and then there's earth like a source, and air guns like a source. Two. So when you do that surface integral on here, P grad G0 minus G0 grad P, and you evaluate it over here, you get the portion, in other words, the total field is due to the air guns and due to the earth. You isolate, you're separating. You can get the wave that's due to the source over here, any point over here in this volume, you get the reference wave. In the earth, you get the reference wave by P grad G0 minus G. So you can predict on your cable the reference wave. You don't have to filter it, you understand? If you have that information. So you're going to see talks here, which right now, in fact, that apply that idea of wave separation for both. So this is a separation of the scattered wave from the reference wave. Okay. There's another wave separation, and we have Dr. Jingfang Zhang, who pioneered that. Yes, here from BP. So that works the way I just said. So there's one separation which deals with the first step. Separate the reference wave from the scattered wave. Next step. Now you have the scattered wave. De-ghost it. Yes? So that's the next application. We went to, for the de-ghosting, we pick a different reference medium. We pick a reference medium of water everywhere. Yes? And then we have three sources. Sources mean terms on the right-hand side. If I make it water everywhere, I got to have some kind of alpha that turn water into air. Yes? I got to have air guns, and I got to have some kind of alpha that turns water into earth. So now I have three sources now. And so, and the Green's function here, since it's homogeneous, no boundary, is just outgoing. Yes? The G0, just direct everywhere. So the air guns as a source send a wave out, the air sends a wave out, the earth out. In other words, they're all this times their whatever rho is. Yes? So that outgoing is then useful, because if we take an integral now like this, let's say we take it like this, and we evaluate it inside of P grad G0 with this G0, okay? Not the one we used a minute ago with the two half spaces, the homogeneous one. Then if you evaluate this on this surface, and you evaluate this inside, P grad G0 minus G0 grad P dot N on this surface, on top it's going to go away from by Sommerfeld, then, and you evaluate it here, you get the contribution to the total field due to the earth, which has to be upgoing, because that guy is always going out, yes, from whatever the sources are. It's outgoing. So what the earth does, so if you evaluate that P grad G0 business, inside, here's the cable, and you evaluate it above, it's always up, because the contribution due to the earth is away with that G0. If, in addition, you evaluate it at a point lower than the source, this is lower than the source, then it is the only up wave. Because this, if you evaluate that output point in the volume at a position lower than the air guns, then the air guns are sending a wave down, the air is sending a wave down, the earth is sending a wave up. You just computed by Green's theorem the contribution due to the earth, which is up. And for that type of position, which is below the air gun, it will be the only up. So that gives you a deghoster, yes? So that's the idea. So that is all developed in Jin-Fang Zhang's thesis, and Dr. Mayen in the back applied that to field data at Exxon and PGS, okay? Okay, so I just said this. Okay, let me just, so there's a form then that does deghosting. If you take that G0D means just direct, just out. If you do this integral and evaluate it above the cable, in other words, in the volume above, you're going to get a receiver deghosted data, and then if you repeat it by applying reciprocity and then doing it on the sources, Green's theorem on top of Green's theorem, you'll do source deghosting as well. The point is, how does this relate to conventional deghosting, yes? If you assume that the measurement surface is horizontal, if you assume that, yes, and you Fourier transform both sides, it reduces to what's called PVZ, conventional deghosting. That form on top, okay? In other words, you get the up wave, the deghosted, is some relationship between P and, because the G0 are analytic, just, okay, and reduces to this form, yes? A well-known form. If your surface is not horizontal, you go to this. If you're at the ocean bottom, yes? If you're on land, you want to do deghosting. If you assume PVZ, you're taking a big chance with wadis, and they do, at their own risk, yes? This gives you an opportunity when it's non-horizontal, yes, to do deghosting at a point above the actual cable. Well, when Jim Mayen was at ExxonMobil interning, they didn't like that idea. They didn't like the idea you're going to give us a new cable that's deghosted. We like our cable, they say. You know, we just like our data. We want our data deghosted, not some new data, okay? So that kind of interest says, can we make that evaluation where it's deghosted on the data itself, not at some, yes? So it turns out that in the Fourier you can. In other words, there's an issue here. In theory, that's not a problem. There's a practical issue with doing it in this domain. So let me point out what that is. These Green's functions that are sitting here are very local. And the closer you put that output point to your cable, the narrower they get. And at some point, the sampling, you got some fixed sampling, you start bringing that output point closer to your actual data, it gets so narrow that you can't sample it, yes? So that has precluded in X omega. So in K omega you can do it. Why? Because you Fourier transformed. When you Fourier transform, you're assuming you have adequate sampling to arrange K. You understand? So, but that's only good for horizontal. So you're going to see advances today due to provided by Jingwu, which arranges for in X omega, which means for a cable that's not flat, to do your deghosting of the data itself. Yes? That's not coming just from Green's theorem. It's going to come from Green's theorem plus a form of wave prediction. Yes? Green's theorem wave prediction, not Green's, a combination of Green's theorem wave separation and then prediction. Yes? Will allow you to deghost your actual non-horizontal cable, okay? I think that summarized what I said. Okay, I think we're, what are the next talks? Does someone have an agenda? I think the next talks relate to this. Yes? It's Jing Wu. Why don't we take a short break? And Jing Wu's, a critical issue is getting these wave separation methods onshore. Yes? So you're going to see Jing Wu's pioneering work on that, and ocean bottom and onshore. Then you're going to see work that deals with non-horizontal, whether it be marine or otherwise, yes? For that, again, you could say, why are you spending so much time in that early part of the chain? It's because the later parts critically depend on that being done well. Okay, so why don't we take a 10-minute break, and then Jing Wu, you can start. Thanks.